Okay, for today, we're going to begin with talking about sets. So sets as a mathematical construction. And so, in a fairly open definition, a set is a collection of objects, and those objects we'll refer to as either members or elements of the set. We will, as variables, we will name sets with capital letters, usually starting at the beginning of the alphabet. The elements will be named with lowercase letters, usually correlating to the set they're from. We will then say that A is a subset of B so we'll look at calling A a subset of B if every element of A so if every let me get this in here right. Oops, that's moving the wrong way. I'm on the wrong screen here. Sorry. If every element of A is an element of B. And we'll do some. So let's do an example here. I'll show you some set notation. I'm going to list every element in A. So I will say, I'll say B is the set of 0, 1, 2, 3, 4. So we'll have the counting numbers 0, 1, 2, 3, 4, and I will say A is 0, 1, 2, and 3. And so A is a subset of B. And we have some notation that we can do for this. What we'll say is A is a subset of B. And so this notation says that the thing on the left is a subset of the thing on the right. Now, there's also a thing called a proper subset. A is a proper subset if A is a subset of B and A does not exactly equal B. So let's look at this definition in a little bit more, and what we'll say is A is a subset of a proper subset of B. And so the proper subset doesn't have the line under it. We can think of this as being very similar as being less than or equal to, in a way. A's elements are in B, and they could be the same. So for a non-proper subset, let's go back to, let's create 4 elements, 1, 2, and 3. A, it's 0, 1, 2, and 3 also. Then an A is a subset of B, and A is also equal to B. And we have this idea of equality that two sets are equal when every member in the set is exactly the same. Whoops, I put not equal. Let me fix that. That's equal. A is equal to B. So this relationship is not a proper subset. A is not a proper subset of B. Now, our original that I defined up here, where A has one less element than B, then A is also a proper subset of B. Now we can talk about the notations that we have. So if I have a set that has no elements, or it's empty, we're going to use that for an empty set. Or a set with no members. Now I can talk about A is an element of set A. So we can say A is a member of set A. So notice this is saying is an element or member. And so we have created some symbology now that we can use to talk about these things. So there's a couple different ways we can talk about sets. I've already started talking about one of these here. Let me change colors here. So I can define a set by listing the elements. Or I can use a rule, right? So we call this list. Or I could also say A is X, where X is a member of the integers, and I put a rule. And so this rule of inequality will generate the same list. And one of the things we're going to talk about is we're going to talk about these sets that we've been using, which is the set of integers and the set of real numbers, because the number sets are the sets that we have been manipulating before. One of the parts of this course is we're going to create some sets of different objects, and so we need to abstract what we were doing with the sets of integers. There's one other things we can do. We can talk about intersections. So if we talk about an intersection of sets, we will write this as A intersection with B. And what it does is it is the collection of all elements X such that X is in set A and X is also in set B. Visually, if this is all the collections of the elements in set A, and this is the collection of all the elements in set B, the intersection are the elements that exist within this space. For the computer scientists out there, this does read like and. It needs to be in A and B. We also have a construction called a union. So the union of sets A and B. We're going to define it as A union B is equal to all X such that X is in A, or X is in B. And if we use the diagram we used before, where I have this being set B, and this being set A. Then in the union is everything in B and everything in A. So let's do an example here. We'll let A be the set of 0, 1, and 3. And we'll let B be the set of 0, 1, 2, and 4. Alright, so if I take A and I union it with the empty set, so I need everything that's in the empty set and everything in set A, well then that's going to be set A all over again. If I take everything that's both in the empty set and in A, well, that's an empty set because there's nothing they share. If I take A union B, I need everything in A and B. So I'm going to get 0, 1, 2, 3, 4. Notice I don't repeat elements. There's a 1 in A and a 1 in B. We're going to say that element 1 is in both of them. Now if I A intersection of B, well, they both have 0 and 1. And so that's what's shared between the two. I can also think of set subtraction. I can take any element that's in B out of set A. Well, I can take 4 out of set A. Well, it's not there. I can take 2 out of set A. It's not there. I can take 1 out of set A, so that goes away. And I can take 0 from out of set A. That goes away. And it leaves me with just the element 3. And so this is how we are going to denote sets. In the next lecture, I'm going to look at the sets that we kind of grew up with, the natural numbers, the integers, and the rational numbers. And real numbers and irrational, we're going to look at numbers.